This meeting is being recorded.
In section 9.3, we're going to look at acidity, specifically of a terminal alkyne. And they ask us to recall ARIO, which, if you remember, the acronym stands for the atom, which has the charge, resonance, if any resonance structures are possible, inductive effects from electron withdrawing groups, and then which orbital will end up housing a negative charge. This ARIO helps us to determine stability of anions. So this was introduced back in chapter 3. So if you do not remember this, you should go back and check this out. So stability of anions, again, can be predicted or explained through ARIO. So we're going to take a look here at when acetylene, which is both the simplest alkyne, but also a terminal alkyne, is deprotonated. So this arrow here is grabbing this proton, right? The base lone pair is grabbing this proton. It deprotonates our acetylene, and then we end up with this acetylide ion. So similar to how chlorine goes to chloride when it becomes an anion, acetylene goes to acetylide. So the orbital explanation is really what we're going to look at here from the orbital perspective. So the O explanation is what we're going to look at here. So if we recall, terminal alkynes have lower pKa's than other hydrocarbons. So that includes the other hydrocarbons such as alkanes or alkenes. So we have a lower pKa value. This means more acidic, right? The lower our pKa value, because it's the negative log of Ka, which the higher Ka is, the more acidic. So the lower the pKa, the more acidic. What we see here is an explanation due to the orbital perspective. An sp3 hybridized orbital, such as with an alkane, all single bonds, would result in this type of anion, which is housed in an sp3 orbital. So this has the most p character. So this negative charge is the furthest from the nucleus here of carbon. So this is the least stable of the 3 different hybridizations we see here. With an sp2 hybridized carbon, the orbital, the length, of the distance between the lone pair and the positive nucleus is less, so this is a little bit more stable, and the most stable would be our acetylide ion or our terminal alkyne ion, whatever it may be. In this case, it is the acetylide ion. So this, again, since it's sp hybridized, it has the most S character, which gives it this shape here and a shorter distance to make it more stable. So we see on this next slide here the relative pKa values. So we see here our acetylene has a pKa of 25. Over here we have ammonia, which is commonly thought of as a base, but it can also act as a weak acid. So that has a pKa of 38. So what we see here is that equilibrium, so we see this double-headed arrow, this equilibrium will always favor the weaker base and acid. So we favor weaker bases and acids. Right, so if you recall, a strong base and a strong acid tend to ionize 100%. So that might help you remember that the stronger the base and the stronger the acid, the more they will ionize, and then we'll retain the weaker acid and the weaker base as our favor in this equilibrium. So what we see in our second acid-base reaction here is we have our weaker base on this side, this hydroxide ion from sodium hydroxide here, and then we have our acetylene right here, and we cannot deprotonate acetylene with hydroxide because this is the stronger base over here, and now our equilibrium is in this direction. So the weaker acid and the weaker base would remain more as products. In this case, the equilibrium favors the weaker. So what we see here on this next slide is this mechanism of how a terminal alkyne can be deprotonated, and they mentioned by a suitable base. So this is the most common base that we'll see here, this NaNH2, but some others may be used as well, and we'll point those out as we come across those. So we have our terminal alkyne, and it's deprotonated by a base. So we have our first curved arrow here that shows this lone pair grabbing that hydrogen, and then the CH bond. Those electrons are moved onto the carbon atom. So this is our alkynide ion that results now. So it's not an acetylide because we have an alkyl group, right? We have this R group. So more hydrocarbons, more CH bonds. So how do we choose a suitable base that could deprotonate our alkyne? Well, we see that these bases up here, so everything above this line here, in base strength, in increasing base strength, so everything above will be able to deprotonate a terminal alkyne. So we have hydride, right? We have this guy here, and notice that the charge is on an H, on an N, on a nitrogen, on a carbon. And what we see below this dividing line here is that these bases will not deprotonate a terminal alkyne, and the negative charge is found on an oxygen. So that's an easy way to remember what types of bases will and will not be able to deprotonate a terminal alkyne. So everything above our acetylide, so everything with carbon, hydrogen, nitrogen, containing a negative formal charge. So that's everything from this section. We'll continue with section 9.4 next time.